Hello and welcome, class, to another lecture here in Chapter 11 of Burge and Overby's Chemistry Atoms First, where today we are going to be talking about the ideal gas law. But not just the ideal gas law, we are also going to be talking about the incorporation of the mole into our previously discussed gas laws. So without further ado, there's a lot to talk about today, so let's just get started. Alright, so far in this chapter, we have introduced 5 gas laws. We've talked about Boyle's law, Amonton's law, Charles' law, Dalton's law, specifically, right, Dalton's law of partial pressures, and Henry's law of solubility. So here we are going to be adding another gas law onto the pile. We are going to be talking about Avogadro's law in 1811. Now, Avogadro's law, published in 1811, was sort of like the next big jump in understanding how these gases, work with each other, how their pressures build, all of the great stuff. So we are still working forward chronologically, and Avogadro's work follows up directly after Dalton's and Henry's. Now, Avogadro's biggest achievement is that he found a method to approximate the numbers of molecules that are present inside of a gas sample using the volumes of the gas. Specifically, I am putting here in parentheses that he was not necessarily using masses of gas. This was a big variance from how the other scientists at the time were working, including John Dalton. They all assumed that mass would be like the key to unlocking the identities of molecules, to being able to count molecules, and in some ways they weren't entirely wrong, but Avogadro was the man who was incorporating volumes into the mix and assuming that the numbers of molecules that we are working with in a gas sample are going to be directly proportional to the volume. All right, I also boxed molecules, right, with that little star. That is because in the era of Dalton, Henry, and Avogadro here in the early 1800s, the concept of the molecule was becoming a little bit more resolute. We were starting to understand that these particles of gases were not point particles, as had been assumed by physics, but rather were their own atoms, their own molecules, their own identities, their own elemental pieces. So we're not quite at the discovery of atoms and molecules as we understand them today yet. Really, that doesn't happen until like the early 1900s, the late 1800s, but the groundwork is being laid here with Avogadro's research. All right, so again, Avogadro's law more specifically states that the increasing amounts of moles, the increasing number of molecules, are going to take up more space, therefore leading to a greater volume V. So here we have another proportional relationship where volume is proportional to the numbers of moles of our gas. So this is really straightforward by today's understanding, by today's concepts. If you have more stuff, that stuff is going to take up more space. So it's a pretty straight linear correlation. Here we have, in the second equation, another form of a gas law equation setting equal to one another, two different scenarios where V1 divided by N1 is equal to V2 divided by N2. And last but not least, we have an updated combined gas law. Combined gas law. Since it does incorporate, we can see Avogadro's law in the mix right here, V divided by N. Now this updated or more, let's say, inclusive gas law or combined gas law is not oftentimes used because we are, in these gas law studies, oftentimes working with closed systems. And therefore, no matter is exchanged. So if no matter is exchanged, it means that we're not actually changing the numbers of particles, and since n oftentimes remains constant in these types of equations, we just remove the n, and this brings us back to the original combined gas law that we had discussed previously. So we're not necessarily going to worry about the more advanced combined gas law in terms of being able to do direct calculations. We could if we wanted to. The equation is simple enough to use. However, I do want to introduce this relationship just because then we can see how pressure, volume, numbers of moles, and temperature all explicitly work together here. This is going to lead us to the ideal gas law in a couple of minutes. All right, just because the number of particles that we are working with tend to not change, because we oftentimes are working with closed systems, it doesn't mean that keeping track of the moles is entirely pointless. There are definitely cases where we are going to need to keep track of the numbers of moles, particularly as we begin working our way to chemical reactions incorporating gases. And that's going to be where we're working our way towards today. All right, so as we work our way towards the incorporation of chemical reactions into the ideal gas law, let's talk a little bit more about how the mole can be incorporated into into the previous gas laws. All right, so let's talk about the mole fraction. The mole fraction of a component, where your component I is going to represent whatever gas you're working with. So this could be carbon dioxide, it could be argon, it could be oxygen, whatever your gas is. This is going to represent component, or it will be represented by the variable I here. So the mole fraction of your component I in a mixture is going to be the number of moles of the component. This is going to be represented by variable n sub I, divided by the total number of moles, which is variable n sub total. Right, so it's just a basic definition of a fraction here. We're literally taking the part divided by the whole, right? The partial piece divided by the total piece. So what's the importance of defining the mole fraction here? Because off on its own, it doesn't really seem to be that useful or consistently useful of a fraction. It's definitely something that could be useful, but like, what's the big take-home message? Well, the big take-home message is, if we are working with ideal gases, or gases in general, and as we just saw, the number of moles can be incorporated into our combined gas law equations, it also stands to reason, due to the proportion of everything in that combined gas law, that the partial pressure of a gas, our partial pressure here, is proportional to the numbers of moles of that gas. Right, if we go backwards to our previous equation, or a previous slide with Avogadro's law, volume is directly proportional to the number of moles that we have. Well, since volume and pressure tend to trade off, we can also say, assuming we're working at a constant volume instead, pressure is directly proportional to the numbers of moles. Right, so the first assumes constant pressure. The second assumes constant volume. But we can assuredly, due to the relationship, the interconsistency of all of these gas laws, conclude that pressure is directly proportional to the number of moles. Well, coming back to our mole fraction slide, if the number of moles and partial pressures are proportional, then we can also say that the mole fraction is going to be equal to the partial pressure of an ideal gas, where this is going to be represented by variable P sub I, divided by the total pressure, which is going to be P total, right? The total pressure of your mixture. Now, we've already talked about partial pressures and total pressures pertaining to Dalton's law, and now that we have also discussed Avogadro's law, we can discuss the incorporation of the numbers of moles as well. Now, the equations below work assuming, again, that we are working at constant volume and also constant temperature, so we want to make sure that the other variables in our gas laws are constant. So the first equation is our first example, or first definition up here, number 1, of the mole fraction, number 1 here, where the mole fraction represented by Greek letter chi sub I is equal to the number of moles of your component divided by the total number of moles. Now, our second definition right here also incorporates pressure into this definition, stating that the mole fraction is also equal to the partial pressure of your component I divided by the total pressure. And in both cases, we can see that the number of moles of I are going to be directly proportional to the partial pressure of I. The total number of moles is directly proportional to the total pressure. So assuming we are working with a situation where, again, we're holding volume constant, we're holding temperature constant, all we need to do is keep track of numbers of moles and numbers of pressures, and let's say hypothetically, if we knew 3 of these variables, we would be able to confidently calculate that 4th missing variable due to the interconsistency of all of these gas laws. So let's do exactly that. Let's take some time to use this new equation that we have to process this information, process Avogadro's law, and how all of these gas laws are so consistent with each other. All right, so let's say we're going to also be observing the atmosphere, the original inspiration for being able to study the gases. We know that the partial pressure of oxygen in the atmosphere is equal to 0.209 atmospheres. Now, assuming the atmosphere has an average mass equal to 5.148 times 10 to the 18 kilograms, so very massive, and this atmosphere also has an average molar mass of 28.97 grams per every mole, let's calculate how many moles of oxygen are there in our own atmosphere, not just in terms of pressures, but in terms of absolute numbers of molecules. How many moles do we have? If you have not paused the video yet, please do so. Try this problem out yourself. But if you've already paused, work through the problem, let's come back together and compare some answers. All right, so let's just gather the information that we know so far. So we can see that we have a partial pressure, right? We're specifically told it's a partial pressure of our oxygen gas. So we're gonna say that this is pressure O2. We are also told that the atmosphere has an average mass. Now, we did not see mass in our mole fraction equation anywhere, so we're probably going to have to do some converting here. We're going to have to work with the numbers a bit. But our mass of the atmosphere is equal to 5.148 times 10 to the 18 kilograms. And we're also told a molar mass. So here we see mole is starting to get incorporated a little bit. The variable that I'm going to be using to represent molar mass consistently throughout the semester is a capital M with a subscript of a W. So molecular weight, molar mass. This is going to be the variable for all of those definitions. All right, so our molar mass of the atmosphere is 28.97 grams per every mole. And we're asked to find the number of moles in the atmosphere. All right, so let's just set up our mole fraction equation first, kind of see what variables we have and what we're going to need. Well, our mole fraction equal to chi sub I, we're not explicitly told to find, but if we were, we could calculate it. Our useful pieces of the equation are going to be the number of moles of I, and in this case, our I is going to be equal to O2. So I'm just going to change these guys to O2 to remind ourselves of what variables are going to go where. The oxygen is the component that we are curious about. All right, there's also an N total that we could calculate. Partial pressure of oxygen divided by total pressure. All right, it seems like so far the only variable that we really have explicitly labeled is this partial pressure of oxygen right here. So we're going to have to figure out what is the actual unknown variable and how can we find the other pieces. Well, we're asked to find the number of moles of oxygen, and this is going to be our variable N sub O2. So N sub O2 at the end of the day should be the only unknown variable, meaning we're going to have to find a way to determine what is the total number of moles as well as what is the total pressure. So let's start with the latter. Total pressure in this case is going to pertain to the pressure of the entire mix. So what is the entire mix we're working with? The entire mix we're working with is the atmosphere itself. So we can also substitute the subscript of total for atmosphere, or ATM, and that would be synonymous. The total is the entire atmosphere. So we can ask ourselves the further question, what is the total pressure of the atmosphere in the unit of atmospheres? 1 atmosphere. Right, on average, the pressure of the atmosphere is 1 atmosphere of pressure. This is something we talked about during the first lecture of chapter 11. So there was a little bit of an implicit piece of information not explicitly given to you. We're definitely making a lot of generalizations in this problem, so our final answer will definitely have some error to it. But since we are making these generalizations, there's no reason why we can't assume that our total pressure in the atmosphere is going to be 1 atm. All right, so that's one variable that we have been able to find of the missing pieces. The last is the total number of moles of particles in the atmosphere. And for this, we're going to need to turn our attention to the mass and the molar mass that we were given in the problem. See, we're also told that the mass that is provided is the mass of the atmosphere, meaning that this is the total mass. So our mass down here is our total mass. And the molecular weight is also that for the atmosphere. So we can use these pieces of information to get out of the unit of the kilogram into the unit of the gram, and out of the unit of the gram and into the unit of the mole. And once we perform these conversions, the number of moles we find are going to be the moles of the total mixture. All right, so let's just set up this conversion. 5.148 times 10 to the 18 kilograms. We're going to need to get out of the unit in the kilogram if we want to be able to actually use our molar mass that has units of grams per mole. So we know that there is 1 kilogram per every 1,000 grams according to our metric conversions. And here's where we can use our molar mass, that there are 28.97 grams per every 1 single mole. All right, kilograms cancel out. Grams cancel out, leaving us only with the unit of the mole, and the final number of moles that we have for the total atmosphere is 1.78 times 10 to the 20 moles. And again, this is going to be equal to our N total. So check, we now have N total, we have partial pressure of oxygen, we have total pressure of atmosphere. This means that all we need to do is rearrange and solve for number of moles of oxygen. In order to do this, what we're going to need to do is multiply this N total up to the other side of our equation, multiply it by this partial pressure of our oxygen here. This will result in a number of moles of oxygen specifically in the atmosphere equaling 3.72 times 10 to the 19 moles. Now this is a humongous number. If we were to go one step further and calculate how many molecules of oxygen are in the atmosphere, this would also be in an even larger, ridiculously huge number. But what's crazy awesome is that we can use equations like this to predict in what ballpark are we going to be? What is the approximate number of molecules, or in this case, moles of oxygen, do we have in the entire atmosphere? And we've talked about already how huge the atmosphere is, how much pressure it actually pushes down on us with. Like, this is incredibly astonishingly awesome that we can calculate this in the first place. The incorporation of the mole into our combined gas laws was the final piece of the puzzle that we needed in order to determine one single comprehensive ideal gas law. Now, Emile Clapeyron in 1834 published these results, again referring to this gas law as the ideal gas law, because we are assuming elastic molecules. We are assuming that each of these atoms or molecules, regardless of size, regardless of geometry, is going to be interacting with not only the walls of the container, but also with each other perfectly. That all of the energy, all of the collisions are not going to be sticky, they're not going to be attractive, they're not going to be repulsive. We are assuming that they are perfectly elastic. Now, with that huge assumption stated as the premise of this entire gas law, what Clapeyron did was combined all of our previously discussed gas laws with Avogadro's in order to find the following. First, we have pressure times volume is proportional to the number of moles times temperature. This proportionality is also the result, right, of just combining all of the gas laws that we have, where pressure and volume seem to come together in the numerator, moles and temperature were together in the denominator. We just multiplied the left denominator up to the right. So here we have this really nice proportion. The question, though, that Emil asked, that Clapeyron asked, was how can we make the left and the right-hand side of this proportion equal? What, is there just like a missing constant that we don't have? Is there another variable that we're not studying? What is missing from this equation? And so to find this, or in order to answer that question, he performed a series of experiments with different gases where he measured the volume of the gas as a function of our moles times temperature divided by pressure. So he took this proportionality present on the left, divided each side by P, cancel out the P's here, and measured our volumes as a function, again, of moles, temperature, and pressure. And what he found was a straight line. Now this was great for a multitude of reasons, but the biggest reason was it confirmed that we were not missing any extra variables. There is nothing else that we really need to pay attention to, again, assuming ideal gases, other than volume, temperature, pressure, and numbers of moles of substance. All right, the second thing that his discovery led us to was the existence of our ideal gas law, the equality down below. In the equation down below, we can see that there is an extra constant present here, this R. Where did this R come from? Well, the R is the result of the slope of this line that Clapeyron was able to find. The slope was equal to the same value R approximately for all of the gases that he was working with. In terms of the construction of our equation, from his graphical results, remember, our function, V, is being studied dependent on n times t divided by p. But that's not all. You see, because we are studying a line, that means that the function that we write has to be of the form y is equal to mx plus b. Well, the intercept, we can see down here, is 0. So our b equal to 0 just ends up kind of going away. We don't have to worry about it. Our x, let's see, is the independent variable here, the n times t divided by p. The missing piece is the m out in front. The m is equal to the slope. And the slope, as I just said, in the ideal gas law experiments was found to be equal to this constant r. So if our slope is equal to r, we now have this new beautiful equation, not a proportionality, but an actual equation. V is equal to r times n times t, all divided by p. Well, to simplify this equation, to get rid of that denominator, all we do is multiply the p back up to the left-hand side, and bada boom, bada bing, we have the ideal gas law. PV is equal to nRT. Now, what can the R equal? It depends on what you're studying. The two forms of R that we are going to be seeing the most commonly is equal to 0.08206 liter times atmosphere divided by mole Kelvin. And this is the form that we're going to be working with, assuming that we're using the ideal gas law or some similar gas law. The other R is going to be the most useful when we are studying thermodynamics. So the motion of gases, the kinetics of gases, the energy of the gases. This alternate R is equal to 8.314 joules per mole Kelvin. So let the units guide you. All depending on the setup of your problem, you can infer which of these R's you are going to need in the ideal gas law based on the units of the other variables provided to you. So are you being given volumes and temperatures and pressures? You're probably going to use this first form of R. Does the problem describe some type of calorimetric setup or speeds of gases, velocities of gases? If that's the case, then you're probably going to use the second form of our equation. And the big difference is the incorporation of the joule. That's going to be your big red flag. If the if the wording of the problem involves energy units, if there's joules anywhere, if there's velocities anywhere, this second form of R is going to be the one that you are going to need. Otherwise, feel free to default onto the first 0.08206. All right, so in our previous example problem, we found the number of moles of oxygen inside of the atmosphere. Let's take this one step further. Let's find what the total volume of the oxygen is in the atmosphere. And in order to do this, we're going to need to know our temperature. We're going to assume an average temperature across the entire atmosphere of 95.9 Kelvin. So here I'm going to encourage you guys to kind of break out the calculators, work through an ideal gas law problem on your own, plug in our variables, solve for volume. All right, welcome back. We are going to be using our new equation, PV is equal to nRT, ideal gas law equation, and we're going to use some of the information from our previous example problem, some information given right here, and we're going to solve for V. All right, so obviously the big caveat is that we are assuming that all of the particles in our atmosphere are going to be behaving as ideal gases do. So let's just pick out the variables that we know. Let's plug them into our equation. Hopefully the calculation is not too bad. All right, so pressure. We need the partial pressure of our oxygen in order to solve this problem. In our previous problem, we were told that the partial pressure of oxygen is 0.209 atmospheres. Be aware, we cannot use the total pressure of the atmosphere if we're trying to figure out the volume of a piece of the atmosphere. We're trying to find the volume of our oxygen, and in much the same way that pressure and number of moles are related, volume and number of moles are related as well. Remember, Avogadro's law. All right, volume is what we are solving for. Number of moles of oxygen, we also calculated as a part of the previous problem. The number of moles of our oxygen was equal to 3.72 times 10 to the 19 moles. The gas law constant R is going to be the 0.08206 liter atmosphere per mole Kelvin version. And how we knew that this was the gas law constant we would need, well, we have units of atmospheres right here. We have units of moles right here. We're trying to solve for a volume. Oh, whoops, moles are right here. And the last piece of information we have is temperature, 95.9 Kelvin. I don't know where that 2 came out of. It just like slipped out of my hand. All right, so we can see that moles, atmospheres, kelvins, all of these things are going to cancel out with the ideal gas law constant R, and the only unit that remains is the liter. So whatever our volume is that we calculate, it will be in the unit of the liter. All right, so the volume that we find is equal to 1.40 times 10 to the 21st liters of oxygen. So this is a humongous volume. Volume's very, very large indeed. So could we have solved this problem just directly using Avogadro's law? Sure. But it's also a really nice way to demonstrate how the ideal gas law can be useful as well. See, all of the previous gas laws require that we know 2 different data points, a before and an after of some sort. The ideal gas law does not require us to know 2 data points. All we need is a pressure, a volume, a number of moles, and a temperature, or some combination of 3 of those 4 variables. And thanks to the ideal gas law equation and the discovery of our gas law constant, we no longer need to be paying attention to 2 data points. Sometimes it's helpful to only have to pay attention to 1. All right, now that we have come to the culmination of the ideal gas law, let's talk about standardized experiments. All right, so standard temperature and pressure have been defined for temperatures and pressures pertaining to gas law studies for modern experiments. This helps us in much the same way as defining standard conditions for all of our enthalpy types of experiments. The only difference here is that now we're looking at temperatures and pressures. So So the standard temperature for a gas law experiment is not room temperature, but rather it is 0 degrees Celsius, which is equal to 273.15 Kelvin. So this is a little bit different than previous standard definitions. The pressure, though, is approximately the same in terms of its definition. Our standard pressure is 1 bar, which is super, super close and basically equal to 1 atmosphere. The reason why we define it as 1 bar in chemistry is because that, again, is the standard unit for measuring pressure according to IUPAC, or the International Union of Pure and Applied Chemistry. All right, so IUPAC says that the standard pressure is 1 bar, and so it shall be. So something that's really awesome about defining a standard temperature and pressure, though, is that due to the behavior of gases, 1 mole of any ideal gas will occupy the same volume, right? PV is equal to nRT. So if the pressure is standard and constant and the temperature is standard and constant, it looks like the only variables that we really have to pay attention to are mole and volume. Well, because our gas law constant is also a constant, this means that by plugging in our standard temperature and pressure, we can rearrange and solve for the volume that 1 mole of gas occupies. And regardless of the gas type, 1 mole of an ideal gas will occupy 22.4 liters of space. Now, 22.4 liters is approximately the size of a beach ball. It's a little bit of a larger beach ball, but assuredly 22.4 liters does fit inside of a kind of standard beach ball shape. So if you're holding one of those standard kind of beach balls, you're holding 1 mole of gas in your hands, assuming that we are at standard temperature and pressure. So we assume that ideal gases are non-reactive mixtures of gases, but what happens when these species do react in some way? Whether a gas be a reactant or a product, we can use the ideal gas law to incorporate pressure and volume into the measurements of chemical reactions. Now, below we have a chemical reaction. Sodium azide, or azide, I've heard it pronounced both ways, is NaN3, and it's normally found in solid form. This solid is a chunk of solid that is normally stored within your steering wheel, and upon collision will be released and actively reacts in a decomposition reaction generating sodium solid, but what we care about is nitrogen gas. You see, this nitrogen gas is what gets pumped into your airbag, N2 gas. For every 2 parts sodium azide solid that is stored inside of your steering wheel, you are going to get 3 nitrogen gas particles as a result of the reaction. So our question is, how much sodium azide do you need to store inside of that steering wheel to make an effective airbag? Do we have the means to calculate that answer? Do we have the means to solve that problem? Well, as it turns out, with the incorporation of the ideal gas law into stoichiometry, which we've been talking about for a couple of chapters now, the answer is yes. Because what these two things have in common, PV is equal to nRT, and stoichiometry is the mole. We can use PV equals nRT to find or work with units of moles of gas. And similarly, stoichiometry is the means with which we can calculate and predict moles of products and reactants, assuming that we know something about the alternate, right? We can figure out moles of products from moles of reactants. We can figure out moles of reactants, assuming we know how much product we made. So let's figure out how much sodium azide is necessary to generate a particular amount of nitrogen, a specific amount of nitrogen, the amount that is going to be necessary to blow up this airbag. So this is the last example problem of the day. It's a little bit more involved because we are tying together our previous gas laws from this chapter with stoichiometry, with real chemical equations, real types of chemical problems. So we're going to be finding how many grams of sodium azide are necessary to provide enough nitrogen to fill a 21.7 liter bag. This is like standard airbag size. Now we are assuming that we want to fill it with a pressure slightly above that of atmospheric pressure, which is going to ensure a rapid detonation and a nice firm airbag upon impact, as well as we're going to assume 27 degrees Celsius, assuming you're keeping the inside of your car a little bit above that of room temperature for comfort, 27 degrees Celsius is a pretty reasonable temperature to be working with. And it may not seem like it, but we actually have all of the information that we need in order to figure out how much sodium azide is necessary in order to complete this task. So I'm going to let you kind of unpack everything that we've been working with so far today, from Avogadro's law to mole fractions to the ideal gas law. All of these pieces of information, all of the gas laws can be used to solve this problem. But we really only need one, PV is equal to nRT, to do it. So I'm going to let you guys kind of parse out the information we're working with. Remember to keep stoichiometry in mind. See if you can't calculate the number of grams that we need. All right, welcome back. Let's talk about the crux of this problem before we just start plugging in numbers willy-nilly. The crux of this problem is that PV equals nRT is the ideal gas law equation, meaning that we can only use it with gases. In our chemical equation, we have two solids and a gas, and PV is equal to nRT is only going to be useful from the perspective of nitrogen. So here's the first real thing that we need to pay attention to. What chemical species are we working with? True, we want to find something out about our sodium azide, but it is the nitrogen that we have to start with, because we're given a volume, we're given a pressure, and we're given a temperature, but each of these things pertains to the nitrogen, not the sodium azide. So if you've already kind of kept that in mind when setting up the calculation, awesome, good on you. Let's set this up together and make sure that we actually found the same number of moles of nitrogen. So our pressure is 1.20 atmospheres. Our volume is 21.7 liters. Number of moles, we're not given any specific value of, totally fine. Gas law constant. Now again, we have to ask ourselves the question, are we working predominantly with the ideal gas law, or are we working with energies? Here we can see we're working with the ideal gas law, so that means that our R is going to equal 0.08206 liter times atmosphere divided by mole times Kelvin, and our temperature is 27 degrees Celsius. Now, if you do remember from previous gas law calculations, the fact that we need to convert into Kelvin, you may have asked yourself, is this still necessary? And the answer is yes. 1, we're still working with the gas law, which means we still need to be working with an absolute scale. 2, we can see that the unit of the Kelvin is present inside of our gas constant R. This is another huge reminder that we need to convert 27 Celsius into Kelvin. So in order to convert 27 degrees Celsius into Kelvin, we're going to have to add 273.15 to it, giving us a grand total of 300.15 Kelvin. Now here we are able to see straightforward value, or straight glance, that we have one equation and one unknown. And again, the unknown that we're finding here is the number of moles of nitrogen, N sub N2. This is not the number of moles of sodium azide, this is moles nitrogen, the gas that we are actually observing. So N of N2, upon rearrangement and calculation, we find is equal to 1.06 moles. Now this is awesome, but it's not what we're looking for exactly. Right now we have found out how many moles of our N2 we have. We want to know how many grams of sodium azide we need in order to make this total number of 1.06 moles. Well, how we backtrack is stoichiometry, right? The proportions, these stoichiometric coefficients in front of our molecular species in the chemical equation. We're currently in the perspective of nitrogen. In order to get out of the perspective of nitrogen, we have to acknowledge that 3 parts or 3 moles of N2 were generated for every 2 parts of the sodium azide, this NaN3, that were used up. I just realized that I forgot the unit of the mole right there. All right, so we're out of the unit of the moles of N2. We are in the mole of sodium azide. Well, why not just take this one step further, since we're asked to find how many grams of sodium azide we actually need to complete this chemical equation. Let's just find and plug in the molar mass of the sodium azide, because that's what we need to convert from moles into grams. In observing the periodic table, we find that the molar mass of sodium azide is 65.02 grams per every 1 single mole. Meaning, if we take 1.06, multiply it by 2, divide it by 3, multiply it by 65.02, we're going to get out of the unit of the mole into the unit of grams sodium azide, and our final answer is 45.9 grams of NaN3 solid. All right, I love this problem because it has real great real-world applications. Namely, if you've never really thought about how your airbag inflates, because I know prior to like studying chemistry and coming across this example problem, I never thought about it, but it's kind of eye-opening to realize that there's not just like an air pump stored somewhere under your dash or in like the engine of your car that upon impact just like rapidly pumps up an airbag. No, this happens by rapid spontaneous chemical reaction. There's sodium azide in the hub of your steering wheel, and upon impact, your car, or rather the car's computer, sends a signal to your airbag, to the wheel, or to your steering wheel, telling this reaction to start. So there's a little bit of a spark that goes in, but the sodium azide is going to rapidly decompose into our nitrogen and our sodium. The nitrogen is going to fill the bag, fill up that airbag, hopefully in the need of crisis, saving your life. So this is a pretty awesome chemical experiment, and we were able to determine, just by using the ideal gas law, and provided the parameters of the airbag and the conditions with which it would need to inflate, like how much sodium azide do you actually need to put into the steering wheel in the first place? Like, this is awesome, awesome stuff. So long as we are keeping track of what variables belong to what, where we are in the chemical equation, we can always use the ideal gas law in conjunction with some gas present inside of the chemical equation, and then following up from the ideal gas law, use stoichiometry, as we did right here, stoich, in order to figure out other factors, other measurements in the equation, whether it be the reactants or some other product. All right, before calling it a day though, there is one last topic pertaining to the incorporation of the mole into the ideal gases that we should talk about, which is the density of an ideal gas. Now, we're not going to be working through any quantitative problem, but I do want to address this equation qualitatively. So first and foremost, the density of an ideal gas is found to be dependent on environmental conditions such as pressure and temperature, as well as the identity of the gas in the form of the molar mass. Now, this equation is derived in the textbook, so I don't want to spend too much time on its setup or its derivation, but suffice to say, density is still equal to mass divided by volume, and we can incorporate the ideal gas law into the definition of the mass, rearrange some variables, and discover that density is also equal to pressure times the molar mass divided by our gas law constant times temperature. Now, with the incorporation of Dalton's law, we had introduced to the conversation the basic observation that our gases, especially ideal gases, where everything is pinging off of each other elastically, tend to form homogeneous mixtures. However, if we upset the balance of the numbers of gases that we have, there is going to be a little bit of heterogeneity to our mixture. One really great example of this is like if you've ever had to do like a radon check in your house. Radon is a radioactive gas that tends to settle in the basement of your house because radon is ultra massive compared to other gases. And so radon tends to kind of like nestle itself down into the depths of your house. It's not going to exist up in the attic or in the upper floors. Maybe it will in very small amounts, to be sure, because it is a gas, but because of its high molecular weight, it's more than likely going to settle down at the bottom of your house. Now, there are other examples of this, but the one I want to talk about today is the Lake Nyos disaster in Cameroon. So this disaster is a really great example as well, like a terrible but great example of how the density of these gases can result in heterogeneous mixtures even on grand scales outside of the house. What happened in the Lake Nyos disaster is that there is a lake up in the mountains and a village down below. Now, this lake up at the top of the mountain was being fed into by carbon dioxide vents from the subterranean geography nearby. So this lake was being filled up with carbon dioxide, and everything was well and good until this lake up in the mountains started to suffer from nearby earthquakes and volcanic activity. So with the tumultuous earth shaking, all of this carbon dioxide was knocked loose out of the lake, and instead of floating away or dispersing evenly in the atmosphere due to its high molar mass relative to the other gases nearby, it actually sank down. Now, this carbon dioxide that was released from the mountain was present in such an abundant amount that it filled the valley nearby, and everyone in this valley tragically suffered from asphyxiation and passed away. So the behaviors of these natural gases being modeled as ideal gases, as perfectly being homogeneous, may not necessarily always be the case. So this is something that we do have to pay attention to, and these problems that we're solving with these chemical equations sometimes may be light and goofy, but sometimes can also be deadly serious, like the previous steering wheel and airbag problem, as well as a problem like this. So it is something that we as good scientists do have to pay attention to, and we have to maintain an awareness of not only our place as humans in the world, but the place of our science and how it can be helpful to further benefit society instead of hindering it. All right, with that, we are going to call today's lecture somberly a lecture. We have another one in the book. So we are nearly done with chapter 11. Today we again discussed the ideal gas law. So this is our PV is equal to N our T type of problem. In addition, we discussed gas mixtures from the perspective of our mole fractions. And last but not least, reactions with gases incorporated our old friend stoichiometry into this type of PV is equal to nRT type of problem. All right, so if you have any questions and you're in my class, do not hesitate to shoot me an email as you are wont to do. If you are not in my class and you come across this video someday, please leave a comment in the section down below. Otherwise, if you have homework, please do your homework. And until next time, class is dismissed.